Hi, Benjamin. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Doing well, thank you. How are you?
Good, good. Studying, yeah, I'm sure it's busy for you guys. I am a little bit tired today because my fiance brought me back a mixed fruit tea kind of really late last night, and it kind of kept me up for a long time. So I am a little bit out of it, but you know, I'll do my best to kind of hang in there, as I'm sure probably all of you guys are probably more sleep deprived than I am. So you know, I have nothing to complain about. Okay, so the plan for today is we're going to finish up the lecture notes on 3D finite element types. So there's just a little bit more to go on mixed meshing. And, you know, mixed meshing is, I think, something that everyone kind of understands already, but I think, you know, just for the sake of completeness, we'll go over that. And then we'll start talking about some practical things with finite elements. And so the next practical topic that we're going to talk about is cost reduction strategies. Okay? And so this is a big one because it's, and it goes pretty well. It goes pretty well with our activity next week as well, right? And so, you know, at this point, you know, you guys understand, you know, what finite elements is and what all the different element types are. Now, I think the challenge for you guys, especially as you guys are starting to work on your final projects, is how do you drive that cost down, right? And it's because it's very easy to take any kind of CAD geometry and just throw it into Ansys, and then just run a simulation on it. The problem that everyone will probably be having is that your mesh is too fine. You know, Ansys will complain there's too many elements, or even, you know, when you're out there in industry too, that, you know, you'll run a simulation and it might take hours or days or something like that, right? And so cost reduction is a very big it's a very big topic, and you know, it's something that you always kind of have to be thinking about, where, you know, you kind of want to be in the sweet spot of, like, you know, I want my simulation to cost enough or to have enough elements such that I get an accurate result, but I don't want to overkill it such that I use too many elements or use too complex of a model such that, you know, my simulation takes like a bajillion years to finish, right? And so there's a sweet spot that, you know, you guys need to be in. And you know, we'll start that conversation now about, you know, how do you get to that sweet spot, and what are some things that you can do to kind of reduce the cost. Yeah. There's a boba sword. Yeah, I heard about that. Yeah, it's there's a big boba shortage. So I'm actually not too big of a boba guy myself. I like fruit teas. I think fruit teas are really delicious, but I usually don't like boba inside the teas. But all my friends love boba, so they're kind of panicking a little bit about the about the shortage. Yeah, so we'll see. Hopefully, it doesn't last for too long because um, um, you know, we need our Asian boba drinks. Okay. Another announcement. So, in case you missed this at the end of lecture last time, there was a request to push back the due date for the homework that's out there right now, and so I pushed that back until next Wednesday. And so the homework was originally going to be tomorrow at 11:59, and so now it's going to be due next Wednesday at 11:59. Right. So now you have the weekend and a little bit of the beginning of the week to work on it too. Okay. And so it should already be updated on Canvas, and so I've seen some people have turned it in already, so that's great, and so you don't have to worry about it. But you know, I know you guys have a lot of other stuff going on right now, and so you know, since you know, my main thing is I just want you guys to finish that homework before the midterm. Since the midterm is not going to be until the following week, you know, I have no problems pushing that back until the Wednesday. Yeah. Okay. So any questions? Are there any questions I can answer before we get started?
I have a question.
Sure. What's up?
So, problem number 1 on the homework asks for the difference between natural and essential boundary conditions. I couldn't find anything about that in my notes, so I'm not sure if I missed it or.
Yeah, good point. So we've been calling them something different in this class, and I kind of flip flop about what I want to call them. And so natural and essential boundary, or natural and essential boundary conditions, that's the terminology used, I think, in some intro level finite elements, but kind of the terminology that's used kind of for more advanced finite elements, and what you'll see more often out there is Dirichlet and Neumann boundary conditions. And so I'll draw the connections for you. And so essential boundary conditions, this is the same thing as Dirichlet, right? And so those are going to be your fixed supports or your displacement boundary conditions. Okay. And so natural boundary conditions, these are going to be your Neumann boundary conditions. Okay? Right. And so remember, your Neumann boundary conditions are things like loads, things like forces, things like heat fluxes, things like that. Right. So boundary conditions that are on variables that are not your main solution variables. Yep. Right. Yes. So there is a second exam, and so it's not going to be next week. It's going to be the week after. And so next week, I'll post a study guide for the exam, and I'll do a midterm review on Friday of next week as well. And there is no final exam. Yeah. And so since the final project, I'm already asking you guys to kind of do a lot in Ansys. I want you guys just to focus on that. Okay. I'm not a big fan of having both final projects and final exams, because then your attention is kind of split in between the two, and I think you guys have enough to worry about anyway. And so I would rather you guys do a really nice job on your final project, really make that nice, make your Ansys analysis nice, because end of the day, like that's what you're going to take away from this class, right? You're going to take away that final project. You're going to have that Ansys to kind of show to employers, or to to show yourself later on, that this is how I know that I know finite elements, and this is how I show to other people that I know finite elements too. Okay, so I want you guys just to focus on the final project. And so after this, after the second midterm, there's going to be no more exams for this class. Yeah. Okay. So any questions? Any more questions before we get started? Okay. All right, so let's go ahead and get rolling. All right, so last time what we finished talking about was the 3D element types, right? And so we went over tetrahedrons, both their linear and quadratic versions, and we went over hexahedrons, both their linear and quadratic versions, okay? And so now at this point, you're introduced to all of like the kind of the basic element types that are available out there for finite elements, right? And so I will tell you that it's not all the element types that are available. And so there's many more out there, but at least you guys have a general understanding. And a lot of the other element types out there are kind of based on the tetrahedrons and the hexahedrons and linear versus quadratic, right? And so we're not going to go over all the really advanced element types, but you should have a good baseline to really start to understand what the other elements do. Okay, and so what I wanted to start with today is with this concept called mixed meshing. And the idea with mixed meshing is to apply different meshing techniques for different parts of your geometry. Okay. Okay. Because we kind of just got done talking about, tetrahedrons, they can mesh any kind of geometry. And if you have kind of a curved complex one, that works well for that. But, if you have kind of a straight kind of, type of a geometry with sharp corners and straight sides, hexahedrons are going to be a lot more efficient for those. Okay. But in reality, you don't, if you have kind of a CAD model, you don't really just have one or the other, right? And so you don't have just all weird stuff or all straight stuff. And so you probably have different sections of your model, or even different parts of your assembly, where tetrahedrons might work better here, or hexahedrons might work better here, or you might need more refinement here and less refinement here. And so the idea with mixed meshing is to apply, is to kind of break up your geometry into different parts and apply the appropriate, the best kind of meshing techniques to those different areas, okay? And in the end, what you're going to get is you're going to get kind of the most accurate solution for kind of the least amount of cost, okay? Right, so this is, we do this since most practical geometries. have many different parts. Okay. And if you mesh those different parts, you know, differently, then you're going to get a better quality mesh in the end with less cost. Okay. Okay. All right, and so let's you know, there's really not much more to it, and we've kind of already seen, you know, how to do this in Ansys. And so in Ansys, all you really have to do is just, you know, make different meshing objects for different parts of your model. Okay. And so let's do just a very quick example here. Okay. And so let's say that we have a 2D part here where you know, it's basically like an L basically. Right? So let's say that we have the part that comes in like this. Right. And so we have a part that looks like this. You know, if we kind of break it up into kind of these sections right here, right? We see that you know, these sections that I'm going to circle in red, right? These sections are very block-like, right? And so this would be great for either a quadrilateral or a hexahedron, okay? And so let's go ahead and mesh it like that. Okay. Meanwhile, the part that we haven't meshed yet, this part is curved, right? And so this would probably be more better suited for triangles or tetrahedra. Okay. And I'm kind of butchering this, but you can kind of imagine, you know, that we fill this area with triangles. And so this would be a case where we choose different element shapes to fit the geometry. So this is one common form of mixed meshing, and Ansys does this a little bit already for you, right? And so if you kind of recall when we're using Ansys and we want to apply a hexahedral mesh, Ansys doesn't give you the option to do all hexahedral, right? And so if you remember, the option that Ansys gives you is called hex dominant, right? And so what that means is that Ansys is going to try its best to fill most of this space with hexes, but for locations where it absolutely can't, it'll transform into tetrahedra, okay? And so this is kind of already built into Ansys already a little bit, but of course, you know, you can also force it as well, where you can say that, you know, this region right here, I want to mesh it with tetrahedrons, and then this region over here, I want you to be hex dominant, okay? And sometimes that performs a little bit better than kind of what Ansys will determine automatically, because as some of you have already kind of experienced that if you try to do a hex dominant mesh, sometimes even that one will fail. Right. Even though you're telling it, you know, you don't have to put hexes everywhere, Ansys will still try to do it anyway and still end up with a failure. Okay? So sometimes you have to do it a little bit manually, just to you know, just to make sure that you get a good mesh out of it. Okay. So any questions on this so far? Okay. And so let's talk about mesh refinement now. Oh, was there a question?
Here's a minor question. So if you can go with hex dominant, is there any reason why, like, you would go with tetrahedrons instead, or is that always better, assuming it'll let you?
Yeah, no, it's a good question. And so when you choose a hex dominant mesh in Ansys, like Ansys will kind of try its best based on what it can see from the geometry to kind of choose areas where it thinks tetrahedrons would look better. But it's not perfect, unfortunately. And so what Ansys is going to be looking at is it's going to be looking at basically features of your CAD model, like, where is the curvature the highest, or what's the radius of curvature in these areas. And so, it does a pretty decent job for most simple cases. But for some cases, it's just going to flat out fail. And so, in those cases where, you're trying to put a hex dominant mesh in there and Ansys is giving you an error, what's likely happening is that Ansys it thinks it can put a hex in a certain area, but it really can't. And so from there, you're going to have to force it to say, all right, here's where I can visually see that, the curvature is high. Let me put tetrahedrons there, and then everywhere else we can put hexes. And so in the cases where, the hex dominant mesh doesn't work, you would have to kind of do it manually from there. Right. And so the other type of mixed meshing technique that we've already used to, but I think it's good to kind of put it in words, is mesh refinement in a local area. All right. And so a good example of this is our very first Ansys activity, right? And so we have our plate with the hole. Right. We knew, we kind of, and now we know this because we've already run the simulation, that we know that the area around the hole, we're going to have some stress concentrations around there. Right? And so since we expect some high stress concentrations there, we want to put a refined mesh in that area because that's going to help us estimate the stresses a lot more accurately, right? And so if you kind of remember, what we did was we applied a refinement on the inner circle, and then it kind of looks something like this. And so I'm going to draw I know probably, this area right here will probably be done with triangles, but triangles are a lot harder to draw. And so I'm going to do it with quadrilaterals. Right. And so what we ended up having was we had a really refined mesh around the hole, which is where we expected stress concentration. And then outside the hole, we had a much more coarse mesh. Okay. So we might have something like this. Okay. And so, we can use a coarser mesh outside of the hole because we don't really expect that much stresses in those areas. And so we can really then concentrate the computational cost around that center region where the stress concentration is happening, right? And so mesh refinement is a very, very common, very popular type of mixed meshing that people use all the time, right? And so, in these situations, it really helps to kind of, look at your problem beforehand and before you hit solve, and to think, where do I expect the stresses to concentrate, or where do I expect there to be a lot of really rapid changes in the solution? And if you can find those areas in your mind, then you can then apply mesh refinement there as well. Okay. And if you can't guess those things beforehand, it's not that big a deal most of the time, because what can happen sometimes that you can go ahead and run your simulation, and then based on the simulation results, you can see where stresses are concentrated. And then from there, you can say, okay, I can see stresses are concentrated in this area. Let me refine the mesh in there, and let me see if the simulation results change. Okay. Right. And so the way that we call that, is we call this an iterative process. And so, this is a good technique for your final projects too, especially since I'm going to have you guys do a mesh convergence test for your final projects as well. And so we'll go over what that is, maybe not next week, but maybe the week after that. And so, applying more refinement and stress concentrated areas is a good way to do mesh refinement. All right, so we'll do one more example here, just because this is kind of more closely related to kind of the work that I've done, which is fluid flow. And so whenever you run a fluid simulation, whether it be finite elements or finite volumes, what you usually like to do is you usually like to apply what's called a boundary layer mesh. And so if you have a, let's say that we have flow in a tube. And so let's say that this is our tube right here, okay? And so what a boundary layer mesh is basically what we want is we want to have better mesh refinement near the solid walls of our tube here, okay? And so basically our mesh would look like this, where next to the walls, we're gonna have a very, very fine mesh. And then that mesh is slightly going to get more and more coarse as you get to the middle. I'm doing a terrible job of drawing this, but basically what you can say is that mesh is refined near the walls. And the reason we like to do this in fluid mechanics is that if you're familiar with the concept of a boundary layer in fluids, basically what's happening is that because whenever you have a solid surface, the fluid velocity has to match what's on that solid surface, right? And so since most of our solid surfaces are going to be still and not moving, what this means is that at the walls here, the fluid has to basically just stop moving. But then very rapidly, as you move away from the wall, the velocity starts to rapidly increase, okay? And then in this thin kind of region next to the wall, you have what's called a boundary layer where the velocity is changing very, very rapidly, okay? And so just like as we saw with the stress concentration, whenever you see the velocity changing rapidly, you want to put a lot of mesh refinement in those areas just to make sure you capture that change really, really exactly, okay? And so that's why in fluid mechanics, you see this basically type of called a boundary layer mesh to make sure that you have really fine elements next to the wall, so you can estimate the boundary layer properties really, really properly. Yeah. All right, question. So how do we apply no slip in that case? So we'll go over fluid flow simulations in Ansys later on this semester, but it's one of the basic boundary conditions that you can apply, and so. Basically, you apply the boundary condition in just the same way, where you click on a surface and you say, I want to apply no slip here. Yeah. But we'll go over it later on this semester. But I don't think no one's doing fluids for their project, and so I think we'll save it for one of the last days, and just so that we go over all the things that'll be useful for your projects, and then at the end we'll go over some things that I think is interesting but not directly applicable to what you're doing. Okay, so any questions on this so far? Okay, so that's mixed meshing, and so I want you guys to be thinking about that when you're doing your projects. And so especially I think a lot of your projects, I think I commented on this for a lot of your projects too, that a lot of you are working with geometries where for large parts of the geometry we don't really care what's going on over there. And so you really want to make sure that you apply your meshing, a refined mesh in the areas which you're interested in knowing, and then for the other parts that you don't care, you can either suppress them or you can do a coarse mesh over there. Okay? And so the quality of your mesh really determines the quality of your simulation. So it's something to really, really pay attention to. Okay. All right. And so the next thing I want to talk about, in terms of practical details, is cost reduction strategies for finite element simulations. And so why are these important, right? And so cost reduction strategies, what I mean by that is basically these are strategies to allow you to get the same accuracy or the same type of simulation results with much less computational cost. Okay. Okay. And so cost being things like the amount of time it takes to run the simulation or the amount of computer memory that it takes up. Okay. And so, you know, the main ones that we're going to talk about for this lecture anyway are going to be when to use 2D simulations. Right. And so there's actually, you know, a lot of practical cases where you can actually do that. Okay. And another topic that, you know, you should be familiar with from before, which is symmetry. Okay. And so we'll talk a bit more about symmetry, about, you know, how you actually apply this in Ansys, and, you know, what are the conditions that you can use to, you know, what are the settings that you can set up in Ansys in order to get symmetry boundary conditions. Okay. All right. And so let's start with 2D simulations, right? Because 2D simulations, you know, obviously, you know, from our first activity, we know are a lot cheaper, and you can actually apply them, you know, in a lot of really practical situations. Okay. And so in cases where you can apply a 2D simulation over a 3D one and still get the same results, you know, it's going to be much more preferable to use a 2D simulation just because it's going to be a lot cheaper. Okay. Okay. And so the first situation where we can use 2D simulations are for cases called plane stress. Okay. Okay. And so plane stress, basically, these are situations where we can assume that the structural stress is constant through the thickness of our structure. Okay. Right. And so this typically happens for cases where our geometry is just really, really thin. Okay. And so thin geometries are ones where the height and the width are much, much bigger than the thickness. Okay. Okay. So any questions on this so far? Okay. All right. So one example that we've done with plane stress is actually our first activity. Right? Okay. And so if you recall from an activity, you know, what we did was we did a simulation on a very thin plate with a hole. All right. right? And so our plate looked like this, right? And the assumption with using this plate was that it was very, very thin. And so if you compare the, we'll call this the width, and we'll call this the height right here, okay? The width and the height of this plate were much, much bigger than the thickness, right? And so if we kind of take a, we take this plate and maybe rotate it on its side so we can kind of look at it from here, right? You know, it might look something like this. Okay, so where this is the top of the plate, and this is the bottom, okay? And so, you know, it's really, really thin, okay? All right, and so what the plane stress assumption basically says that if we measure, you know, at the same kind of XY positions, as we call this X, we'll call this Y, okay? If we measure the stress at one XY location, both on the top of the plate and then maybe right below it and right in the middle, okay? Right, at all of these locations here, then the stress should be the same. Okay. In addition to that, you know, if we say that, you know, the XY directions are in the plane here, and we say that the Z direction is standing straight out, what we can assume here is that there's going to be no stress in the Z direction. Okay. Right. And so that's basically the conditions for plane stress. And so for plane stress, you need to have you know, stress all the way around, or you know, in the same XY position that has to be the same all throughout, and then there has to be no stress outside of the plane as well. Okay. And so in these cases, you know, we can basically just approximate it as a 2D structure, just like we did in you know, in the first activity, and then we'll be able to get the same results, you know, with much less expensive elements, right? And so if you say that, you know, if we mesh this geometry with quadrilaterals versus hexahedrons, you know, the quadrilaterals per element is going to be a lot cheaper than the hexahedrons ones, okay? And you can almost think of it like this, where like, say that we did try to model this with hexahedrons, right? So let me put a hex right here. Okay. We're kind of doing, you know, you can almost think of it like twice the amount of work, right? Because if we if our, you know, plate has some thickness here, then we have 4 nodes on the top and 4 nodes on the bottom, right? But if we ran the simulation with quadrilaterals, you know, we're only going to have 4 nodes per element, and so, you know, on a per element basis, you know, we're running at half the cost, which is huge, right? Anytime you can knock off half the cost, that's a huge, you know, a huge significant increase in performance. Okay. All right. And so this makes sense, right? And so, you know, kind of, I guess the assumption with 2D simulations is that, you know, they're basically paper thin, right? And so that's why we call them 2D. And so if your structure itself is already, you know, very, very thin, at least relative to some of the other directions, it kind of intuitively kind of already makes sense that, you know, we can do this with a 2D simulation, you know, and work with it just fine, okay? And next week when we do Ansys Activity 5, we're going to take this a step further. We're going to introduce something called a shell element. Okay. And so a shell element is a special type of element for these thin types of structures, right? Because most of the time, what you'll encounter in practice is that, you know, you're not going to be doing just a simulation on a simple, you know, flat plate like this, right? You're going to be doing simulations on very complex structures, like maybe like a bridge or something, where certain parts of that bridge are very thin. Okay, and so for the parts that are very thin, you know, you can transform just those parts into a 2D problem. And the way that we do that is we use something called shell elements. Okay. Okay. So any questions on this so far? Okay. All right. And so that's the plane stress condition. And so remember, plane stress just applies to any kind of thin structure. And so now let's go over a plane strain. And so plane strain is another another situation where we can apply the 2D we can apply a 2D simulation, but this plane strain assumption is actually, you can almost think of it as the very opposite of plane stress. Okay, and so in plane stress, where we're able to apply it for very thin structures, plane strain makes the assumption that our structure is very, very thick. Okay. Right. And so most common you would see, the most common way that you would see the plane strain assumption being used is for a cross section of a long vessel. Okay. Okay. And so let's say that we have a beam that's very, very long. Okay. And so in the direction that's going into the page, we're saying that this beam is very, very thick, right? And so instead of simulating this entire beam, where we can kind of make the assumption that every cross section is going to be the same, what we can do is we can just do the simulation on just the cross section. Okay. And so from this, we can basically assume that because we're only taking a cross section of the structure, that all the strains and deformations only exist within the plane of the analysis. And so basically, we're not going to have any significant displacements outside of this plane, right? That's either going up from the plane or down from the plane, right? And so we assume that all the displacements are kind of the same, and it only takes place within that plane. Okay? And so that's why we call this plane strain condition. Okay? And the reason that we can make this assumption is that we're only taking a cross section of this, right? And so in reality, you're not, the structure doesn't have just that cross section. It has all the material kind of before the cross section and all the material afterwards. Okay? And so basically the assumption here is that because there's the other materials everywhere out there, then the other parts of the structure will kind of maintain that it doesn't displace in that direction. And so you can imagine that they're basically kind of holding this plane in place. Right? All right, question. So is there a specific thickness criteria that classifies an object as thin or thick enough to use a 2D simplification? Yeah, no, it's a great question, and it's got to be something that unfortunately is kind of problem specific, and because it depends on the loading as well, right? And so if you have loading such that you kind of expect there to be a gradient of stress throughout, and so let's take kind of a thin case as kind of example. And so for a thin case, let's say that we have a beam, and it's kind of thin like this, okay? Right? And then we're trying to see, you know, can we use a 2D simulation for this beam, right? I would be very hesitant to do that if you had a situation where the loading takes place like this, right? And so if you have a beam that's in bending, right? And what do we know about bending beams? And so we know that when a beam bends, right? Exaggerated look, it might look like that. What you're going to have is that the top of this beam is going to be in tension, while the bottom of the beam here is going to be in compression, right? And so in that case, you have a big change in the stress, as you go through the thickness of the beam, okay? And so in that situation, even though geometrically the beam itself might be very thin, I would really hesitate to use a 2D simulation for this, because you have that gradient of stress that goes throughout, right? So you go to basically maximum tension to maximum compression in that very short amount of time, right? And if you run a 2D simulation, you're just going to lose all that data just altogether. And so, unfortunately, it kind of depends on the situation. Just kind of go based on kind of the logic that we have here, where if you basically expect the simulation to be, stress same all the way through the thickness, then you can use a 2D simulation for that. And then for plane strain, if you can reasonably make the assumption that there's going to be no displacement into or out of the plane, then you can use the plane strain assumption for that as well. Okay. So any more questions on this? That was a great question, by the way. Okay. And so schematically, for the plane strain, it looks something like this, right? And so let's say that, we have our thick member, and I'm just going to cut a slice of it. And so our plane strain simulation might be done, in a very thin slice like this, okay? But in reality, what we have is, the structure is kind of surrounding it all around, right? And so even if this plane right here wanted to displace, into or out of the plane, the other parts of the model will be like, no, we're still here, and we're not going to let you displace, out of your plane, okay? And so this is kind of the reason why, for very thick structures where you have, lots of other material to kind of hold it in place, you can just analyze a cross section as a 2D simulation, okay? All right. And so just like you saw with plane stress, that if you can apply plane strain, you're gonna get a much lower computational cost, which is always a good thing, and you're not really going to sacrifice any of the accuracy as well. Okay. Okay. Right. So that's plane stress and plane strain, and so be on the lookout for those cases, because if you can run a 2D simulation, that's always going to be way faster than a 3D one. Okay. And so for cases where you can do that, it really saves you a lot of stuff. And so for your projects, I don't anticipate too many of you being able to do that, but it's kind of good just to know, just kind of in general for after this class. Right? Okay, and so now let's talk about the other main way that you can make a big reduction in cost, and that's through symmetry. All right, and so we've already talked about symmetry, and so I think everyone's familiar with this, but symmetry is basically a technique that you can use to cut your model at certain locations, and only do basically half the work. Okay. All right. And so in order to apply symmetry, as we kind of learned before from the beams and truss unit, that both the geometry and the boundary conditions have to be symmetric across your symmetry line. Okay. And symmetric, what that basically means that it looks, if you kind of cut your model in half, the model looks the same on one side of the cut as the other one. Okay. And so let's take our first Ansys activity as an example again. Okay. Right. And so there's our plate with the hole. And then we're pulling it here with some pressure P. Okay. Where P is just, it's not a pressure, I guess. It's a distributed load. Okay. And so what we can do instead of simulating this entire thing, what we can do instead is we can cut this in half. We'll cut it in half this way. Okay. And then we only have to do the analysis on that half of the structure. And then we're going to get the exact same results, on the other half. We just kind of have to use our imagination to kind of transport the simulation results from one end to the other end. Okay. And remember, the thing that we had to do to make sure that our symmetry was applied properly was we needed to apply a roller constraint on the plane of symmetry. Okay. And because remember, the big tenet or the big kind of assumption with symmetry is that you don't have any displacement or you don't have any kind of interaction going through this plane of symmetry, right? Because if the situation were changed, just that maybe the loading was pointed down, and then you have part of the structure kind of displacing through that symmetry plane, then the symmetry is no longer going to apply, right? Because then if you have the deformation going this way, then the bottom is no longer going to look like whatever's on the top, right? And so it really has to look like kind of a mirror image on both sides. Okay. Right. And so this is big, because if you can apply symmetry to your problem, you're cutting your simulation time in basically half, or your simulation costs, which is huge, right? And so anytime you can cut things in half, it's just like you're going for groceries, and that manager special pork that looks kind of jank, but it's 50% off and you can't resist it, you buy it anyway because it's good, right? All right, question. So how do we know what direction to put the roller? And so it's always going to be perpendicular to the cut. Yeah. And so it's basically just to make sure that you don't have any displacement going into that plane, right? And so for 3D, think of it as like we actually have symmetry planes there, right? And so you want to make sure that when you apply a symmetry condition, your structure is not going to move into that plane or move away from that plane, because if it does that, then it's no longer symmetric. And so that roller constraint has to be kind of perpendicular to wherever you're going to make your cut. Yeah. All right. All right. And so just like just like we've seen before, both the geometry and the boundary conditions have to be symmetric. And so in this case, making a symmetry cut like this vertically through the plate wouldn't be valid, because on the left side we have a fixed constraint, and on the right side we have our pressure boundary condition. And so this would not fly, right? And so we wouldn't be able to to apply the condition here. All right, question. So is there a way to apply the cut in Ansys without having to redesign it in SolidWorks? Yeah, no, that's a great question. I think there might be a way inside Design Modeler, or actually Ansys comes with another CAD software too, which we're going to use next week, but I've kind of blanked on the name. And so I think those CAD softwares might have capabilities to kind of cut through the space plane. Yes, thank you. Those might have capabilities to cut through the model, because symmetry is something that you want to apply a lot. But I personally haven't done it before, but that's something good to look up. And so I think I'll look into that, and maybe by next week or maybe the week after, then I'll show you how to do it. Yeah, because it is really helpful, because if you have to go back into SolidWorks every time you want to redesign, then that's definitely very inconvenient. Yeah. Mm-hmm. Okay, so any questions on this? Okay. So typically, we look at symmetry and we see it, as a way just to cut it in half. And sometimes, people are kind of happy with just that, right? And so if you can apply symmetry once and you cut your cost in half, then, most people are pretty happy, and you should be happy. But there are also situations where you can apply more than one symmetry cut to cut your simulation cost even more, okay? And so this is something good to be on the lookout for, because it's, half off is great, but 75% off is even better, right? Because that's usually the threshold that I usually wait for to buy games on Steam. So I wait for 75% off, and then I buy it, and then I never play it, and then it just takes up space. Right? And so let's look at a situation for our plate, where now, instead of having a fixed constraint on the left, let's say that we're applying the same kind of distributed load boundary condition on both sides. Okay. Oh, I forgot the hole. And so on both sides, we have a pressure P, right? And so this would be a situation if you're the Hulk and you're taking the plate and you're trying to kind of rip it apart. And so it's kind of the same on both sides. Okay. We've already seen that, we can make a symmetry cut, this way, right? Okay. And that cuts our simulation cost in half, which is great. But since, we also have symmetry, going this way, we can cut it in half there as well. And then, and from there we cut our simulation cost by 3/4. Okay. And so that's really good. Okay. And so, after you apply these symmetry cuts, in the end, you're just going to simulate kind of one quadrant of this geometry here, right? Where you would have, the pressure P obviously on this side. Okay. And then you would apply the roller supports on these surfaces here, because these are where you applied your symmetry cuts. Okay. All right. One quick note here that, I remember, when we talked about symmetry when we talked about beams and trusses, we talked about, whenever you make a symmetry cut, you have to split the load, right? But those were only for cases where we had a force for a load. Yeah. Right. Yes. And so, you have to be careful about the type of load that you have, right? And so in this case, in particular for our first Ansys activity, this P here was a pressure, where a pressure is nothing more than just a force distributed over an area. Okay, so this would be force divided by area, right? And so because we have that area in the denominator already, and because this load is distributed, that load is automatically going to update by the fact that you only have, half your geometry or a quarter of it left, okay? And so, just kind of be aware of that, when you're splitting the loads, you have to be kind of aware of, what type of load am I splitting? Am I splitting like a force, right? And so if it's a force, you do have to cut in half, because, that force is only going to be distributed on half that geometry now. And so you split that force in half, okay? But if it's a type of load that's already distributed, like a pressure or a distributed force, then you don't have to have it, because it's, it's already defined in a distributed way, okay? And so that's how you would, what you would do if you would have a structural simulation. But, you can apply the same things for like thermal simulations as well, right? And so for thermal simulations, we have two types of load boundary conditions that we can do, right? And so we can apply either a heat transfer rate, okay? Okay. Where this has units of power, and so it has units of watts, okay? And so if you're applying a heat transfer rate, you would have to split that if you're doing symmetry, because you're only applying heating on one side, right? or you're only applying the heating on just kind of a small portion of it now. Okay, but actually, what's more common in thermal finite elements is that you apply any kind of external heating as what's called a heat flux. Right? And so heat flux usually has the a symbol Q double prime here. Okay, and so the units for heat flux are going to be watts per meter squared. Okay, and so it's basically power over area. And so in this case, heat flux is already kind of a distributed quantity, and so in those cases you don't have to split it in half. Okay. All right, question. So do any of the activities have a thermal component to them? I don't have an activity plan where you would turn in something with thermal, but I do have an in-class demonstration, an in-class example where I'll show you how to set up a thermal simulation in Ansys. And so that's more of a kind of like, you can watch me do it, and if you're interested, you can follow along. But if you're not doing thermal, then you can kind of just tune out. And so usually it's a kind of a small percentage of the class that does thermal simulations, and so I have it kind of as like an in-class optional activity, and so it's nothing to turn in. Yeah. And so for those of you that are have a thermal component to their final project, I think I already gave you the PDF for that demonstration as well, just so you can kind of get started. Yeah, but I will demonstrate how to set that up later in the semester. Okay, so any questions on this? Okay. All right. And so actually, there's when you're applying symmetry in 3D, you have to be a little bit careful on the roller supports that you apply as well. Okay. In particular, in 3D, what can happen is not only can your structure deform into your plane, it can also rotate into your plane of symmetry as well, right? Because remember, whenever you make a symmetry cut, what you want to prevent is you want to prevent any kind of you don't want any part of your structure to pass through that symmetry line. Okay. Right. And so the main way that we know that structures can pass through it is if it just simply displaces or simply deforms through it. Okay. But another way a 3D structure can do it is that even though you might not have any kind of stretching or any kind of deformation, your structure can still kind of rotate into that plane, right? And we want to prevent that because that's not good too. Okay. My iPad is overheating right now. Too much work today. Okay, and so just as an example, let's say that we have our our kind of half plane structure here, or quarter plane. Okay. And so let's say that we have a symmetry plane right here. Okay. Right. If this structure were to rotate, right, and so no deformation at all. And so usually when I say deformation, what I mean is strain type deformation, right? And so no strain at all. But the structure here might the whole thing might kind of rotate that way, right? And so if it starts to rotate counterclockwise or clockwise in this case, then it's going to pass through the symmetry plane. Okay. iPad is being crazy right now. Okay. And so so when you apply your symmetry boundary conditions, you not only have to prevent displacements, but you also have to prevent all the relevant rotations as well. Okay. Okay. All right, and so I have a nice table on the next page here that I can show you to basically guide you on what rotations and what displacements that you need to fix in order to make sure that your symmetry conditions are going to be satisfied. Okay, and so in theory, you wouldn't need these kinds of conditions here, because if it's already kind of naturally symmetrical, then then it wouldn't pass through anyway. But it's like you need to put it in there anyway, just to kind of prevent, just to really make sure that nothing will happen. Okay. Okay. So any questions on here on this?
So how do you prevent the rotations? I'm not entirely
So
sure I
there's
understand.
yeah. So there's an Ansys type of constraint that you can apply on rotations as well. And so you need to apply not only the displacement type of boundary condition, but also on the rotation type of constraint as well. Yeah. Okay, and so let's go over that table. And I think we'll end a little bit early today because that's all I got planned, right? And so in 3D, let's say that we have three options for symmetry planes here. Right? And so we have the XY plane, right? We have the YZ plane, and then we have the XZ plane. All right. And so we're going to have six other columns here. And so we're going to have one for each of the types of displacements. Okay. Right. And so TX, TY, and TZ, these are all the deformation components or displacements. Okay. And then we also have all the rotations as well. And so we have Rx, Ry, and Rz. Okay. And so these guys are the rotations. All right. And so if your symmetry plane is in the XY, then we can allow any kinds of displacements in the X and Y directions, right? And so we can leave these ones free, okay? Right? And so anything basically in the XY plane, we can allow that to move. But we can't allow any displacements in the Z direction, because any displacements in the Z direction will cross over the XY plane, right? And so we need to fix this, or we need to basically prevent any displacements in that direction. Okay. Right. And so just to kind of illustrate that one for you guys. And so let's say that this is the XY plane right here. Okay. And so we have X and Y in the plane. Okay. And the Z direction would be kind of vertically upwards like this. Okay. And so if we have any displacements in that Z direction, that would violate our symmetry rules, here, okay? Okay, and so now let's talk about the rotations. And so rotation in X basically is any kind of rotations where X is the axis of rotation here, right? And so if X is this axis of rotation, then, things can rotate within the plane, right? And so we need to fix this. And so that we don't have any rotation in that along that axis. And same thing for the Y, right? And so we can't have any rotation about the Y axis, because that's going to go straight into our symmetry plane. But we can rotate with the z-axis here, because if we rotate in z, like around this one, then we don't cross over into that plane at all, and so we can leave this guy free and not have to worry about it. Okay, and so now let's do the same thing for the YZ plane. And so for YZ, we can allow displacements in the Y direction and the Z direction, because that's the plane that we're cutting on. But any displacements in the X direction, we have to prevent that, because that's going to cross over the plane. Okay. And kind of following the same trends as the previous one, what we can say is that the rotations about the Y and Z plane, or Y and Z axes, we have to fix those, otherwise you're going to get rotations into the plane. But rotations in the along the x-axis we don't really care about, because that's not going to violate our symmetry rules. Okay. All right. And then finally, let's look at the xz plane. And so for the xz, we're going to fix translation in the y direction, because that's that's going to crash into our symmetry plane. Okay. Meanwhile, we can leave displacements in the x and z directions. Those are fine. Okay. Meanwhile, rotations in x and z, we have to fix those to prevent any kind of crossing over into the symmetry plane. But we can leave rotations along the y-axis perfectly fine, because that's not going to crash into our plane. Okay. All right. And so if you're kind of confused about how to apply the symmetry conditions, this table will help you out. And so this will tell you exactly what you need to constrain, just to make sure that your symmetry conditions are going to be satisfied. Okay. All right. So any final questions on this before we wrap up for the week? All right. All right. So that's all. I have planned for today, and so I'll let you guys out a little bit early. So I know a lot of you guys have midterms, and so hopefully you guys are taking care of yourselves and sleeping, because it's I know it's stressful, but health is always going to be the most important thing, right? Okay, so hope everyone has a good weekend. Remember the homework deadline has been extended until Wednesday, so hopefully that gives you a little more breathing room, and then I'll see you guys next week.
Okay.
Thanks, guys.
Thank you. Have a nice weekend.
Thanks, you too. All right, Darren, did you have any other questions?